Last week one of my computers went out of disk space, and that came a little bit as a surprise to me because I just purchased it 6 months ago. So I decided to do a little digging into the file system. But as it turns out, if you're in Windows, there are not too many good tools available in order to do this kind of file system analysis. And of course, yes, you can download something from the internet, but they might bombard you with advertisements or even worse, install things in your file system that you don't want to have. So I thought maybe with my basic Python knowledge, I would be able to write something that performs the task of scanning the file system. And it turns out with just 50 lines of Python code, you can actually come up with a file system scanner that is pretty effective and has a really nice visualization along the way. And that's what we're going to be building today. As usual, you should at least have some basic Python knowledge in order to follow. And with that out of the way, let's get started. So first let me show you the milestones of today's video. First we will set up our environment, then we will scan the file system using os.walk. We will create a data frame that will contain all of our scan results, and eventually we will build a sunburst chart from the scan results. Now, as I already mentioned, I'm on Windows here, but all the coding and all the steps will be exactly the same regardless of whether you are in Windows, Linux or Mac. Also, I will be using PowerShell to do all the environmental setups as well as to run the code, and I will use Sublime Text as an IDE. But again, you can use whatever shell you prefer and of course whatever IDE you want to use to write your code. In order to create an environment, you open the shell and you navigate to your project's path. Feel free to use any path that feels convenient to you. In here, you create a new project folder called ScanDisk. This folder will contain all your future project files. You can now cd into this folder, and you can use the ls command to verify that the folder is empty. Now clear the screen content and install your environment by typing pipenv install followed by the 2 strings of the libraries you want to install with it, in this case pandas and plotly. Pipenv will now start to install the libraries together with the environment. Once the installation has finished, you have to type pipenv shell in order to activate your environment. After that, clear the content of your page and you're good to go. You can use a text editor of your choice now to create a .py file. This is a Python file that will contain all your future Python coding. Before you actually start coding, save the file into your projects folder using a meaningful name. In our case, we will save it under the name scandisk.py. Once the file has been saved, we can start doing the imports. We first import the OS module, then we import pandas as PD, then we will import plotly express as px. Make sure you use a dot, not a dash. And lastly, we will import argparse. Once we have completed the imports, we can create 3 boilerplate functions, each of them representing a distinctive activity within our file system scanner. The first of these functions is getSize, which will take a data frame and a file path and return the sizes of all the files found within the file path. The second of these functions is makeSunburst, which will create the actual chart from the data frame that has been passed into it. For the moment, we will just return true. And the third of these functions is the analyze function. This is the main function that runs our code. It will get the file path, and for the moment again, we will just return true. Eventually, we will run the program by calling analyze from within a name equals main statement. However, for the program to be able to run, it needs to know what file path actually is, and we have to pass file path into the program at runtime. In order to do that, we create a parser using argparse and argument parser, and we will give it a meaningful description in order to allow future users to understand what the system is actually doing. So in this case, we type scans and visualizes your file system. Once the parser object has been created, we can add an arbitrary amount of arguments to it. However, in this case we will only add one argument, -p, indicating that the subsequent string represents a path object. We will also add a helper string that indicates to future user how to use the -p argument. Finally, we will create a variable file path to which we will assign the value from the argument p that we have submitted to ArcParse when we ran the program. We are now at a point where we are able to run the program. However, since it's not doing anything yet, we will add a print string within the analyze function. We can now return to the shell and type Python followed by the name of the Python module followed by -p. Then we can copy the file path from the file system, and behind -p we add an empty string followed by the double quoted file path. And if we run that now, Python will take and print that file path which we have passed in. With all the boilerplate out of the way, we can now create a list that will contain all the files from our file path. To do that, we create a variable files and we assign it a list comprehension that will use os.walk to walk recursively over our file path. It will take file path as a parameter and return a tuple of 3 values, with the first value being the path it's currently in, the second all the directories found within that path, and the third all the files found within that path. We will use os.path to join all the paths found together with all the file names found. However, because all the file names still exist in that list fs that you can see here, we have to loop over fs by adding for f in fs at the end of our list comprehension. We can now move the print statement down below our newly created variable and change file path to files in order to print the result. If we now rerun the program, Python will print a nice representation of all the files found by os.walk. As you can see here, all the files returned contain the drive letter as well as the directories that point to our file path. However, we only want to see the files and directories within our file path, so we have to remove all the directories that point to it. In order to do that, we create a variable startdir, and if we use os.path.baseName, it will split off the lowest directory from our file path and assign it to startdir. We can now use our new variable startdir to remove all the pointing directories from each and every file within files. And we do this by typing f.replace, and we replace the file path with the start directory. And as I mentioned, we do this for each f in files. We now move the print statement below the cleaned version of our files list and rerun the program. We can actually see the difference. As you can see here, our returned file strings do not start with the drive letter anymore. Instead, they start with this enumerated Python directory that is exactly the lowest directory from within the file path that we have passed into the program. The next step is to split these strings by their respective path separator, i.e. a backslash or a forward slash, depending on your operating system. This process will replace the strings by lists which contain the relevant directories pointing to the files of interest. We do this whole process because in our next step we will pass the resulting lists into a data frame in which each individual level of directory has to be represented by a separate column within the data frame. The next step is simple and straightforward. We assign the list to a data frame by typing df equals pd.dataframe and then pass the list into the data frame constructor. This will return a pandas data frame, and we can print the data frame by changing the print statement from files to df. If we now return to the shell and rerun the program, the return will be a data frame created by pandas. These non-values result from varying path lengths, and you can ignore them for the moment. As you can see here, pandas has automatically indexed the columns of the data frame, with each index representing the distance to the start directory, which is the enumerated Python directory at index 0. We can now continue to work on our getSize function, which will take a data frame and a file path, and it will return all the sizes for all the files within the data frame. The first step is to create the return value, which is an empty list called sizes. We then will loop over the data frame to construct all the file paths to the individual files. We do that by typing for index, row in df.iterRows. IterRows is the way to iterate over a data frame, which will return a series for each individual row. We can then do row.dropNA to get rid of all the non-values within each series. Because we're not reassigning row to a new object, we have to pass in the parameter inPlace equals true. The next step is to create the file path to each individual file to get the statistics for. We do that using os.path.join, and we join the file path as well as the joined columns from the data frame for each individual row. Remember that our enumerated Python directory exists in both the file path as well as the data frame. So we have to remove it from the row before we actually join file path and the row. Finally, we get os.stat from the size path, and we append the result to sizes. So we type sizes.append os.stat for size path, and from the resulting object we just select st_size. We then have to call our getSize function from within the analyze function, and to do that we go down to the analyze function right below where we created the data frame, and we create a new column by typing df sizes equals, and then we call the getSize function passing in the data frame and the file path. We can now rerun our program, and as you now can see, we have a new column added to the end of the data frame that contains the file sizes for each individual path. Lastly, we have to complete our makeSunburst function, which will take the data frame and create the visualization. The first thing is to create a visualization object called Fig, and we assign to that px, which we imported at the top, .sunburst, and we give it a data frame as the first parameter. The second parameter is a resolution path for the hierarchy that the sunburst chart has to resolve. This consists of all the index columns within the data frame. Finally, we also have to give it the values that it has to display within the chart, and that is the last column of the data frame called sizes. We then just say fig.show in order to display the visualization. As with our getSize function, we also have to call the makeSunburst function from within the analyze function. And we do that by going down right below the print statement, and we type makeSunburst here, and we pass in the data frame. Please note that there is a typo here in line 15. The index actually has to be -1 because we want to select all the columns from the data frame except for the last one. And also here in line 23, we actually need to sort the resulting files list because we want to allow Plotly to do a group by on the aggregated folders to come up with aggregated folder sizes. If we now rerun the program, we will get exactly the same result, but also a browser window will open and display the Sunburst chart. And you can see that we have some mouse over tooltips here that show additional information, and we can, by clicking on the separate fields of the chart, drill down into the chart, and by clicking into the center we can drill upwards in the chart. Now notice that right now this chart looks a bit messy because we're including all the files within file path, but with just some minor modifications you can actually limit your search in a way that you can precisely select the file type that you're looking for, as for example JPEG files. In order to achieve this, we have to return to our script and create another parameter file type. The indicator for a file type will be -t, and we will add a default string in case we don't enter a parameter. In this case we will just take a dot, and I will explain later why a dot is sufficient. We also changed the help string to -t and file type. And then we will duplicate the line that parses the argument down below. And this time we parse t, and we will assign the result to the variable file type. Now we have to pass file type into the analyze function call. And also within line 20 in the analyze function definition, we have defined file type as a function parameter. Now in order to make file type work, we go to the first line of the function, right to the end of the list comprehension, and we add a condition here saying if re.search, and we pass in the file type and file f. At the top of the script, we import the re module, which is the Python module for regular expressions. If we now rerun our program without modification, we will get exactly the same result as before, because remember, we defined a default value that kicks in case we don't enter additional parameters. Now the default is a dot, which in regular expression terms means select everything. So I would expect to see no difference to what we have seen before. If, however, we now rerun the script and enter an additional parameter -t, and let's say this double quoted string of JPEG extensions, as you can see here, and we rerun the script now, then our Sunburst chart will be limited to only JPEG files. And as you can see here, only JPEG files have been selected. This functionality offers all the power that you have through regular expressions, so it's not just extensions you can search for, but any kind of patterns within your files. Please like the video if you enjoyed it, check the channel for new contents, and see you next time.